Hi, welcome to Space Station Alpha. I'm Commander Bill Shepard, and these are my fellow crewmates, Flight Engineer Sergei Krikalev and Soyuz pilot Yuri Gidzenko. And right now we're orbiting 230 miles above the Earth. On today's NASA Connect, you'll learn how NASA researchers are working together with international resources aboard Space Station Alpha. You'll observe NASA engineers and researchers using math, science, and technology to solve their everyday problems. Plus, you'll get to construct your own model of the space station and check out an interactive website that's out of this world. So stay tuned and hop aboard for another exciting episode of NASA Connect.
Wait, I think I see them.
There they go.
Wow, they're traveling pretty fast.
They sure are. Thanks, guys.
Bye.
Hey, did you know that the space station is orbiting our Earth right now? And it's so big that sometimes you can see it travel across the sky.
That's right. Later on in the show, we'll tell you how. But first, welcome to NASA Connect, the show that connects you to math, science, technology, and NASA.
This is Tranquility Park in downtown Houston, Texas. I'm Jennifer Pulley.
And I'm Van Hughes.
Now, before we start the show, make sure your teacher has the lesson guide for today's program. It can be downloaded from our NASA Connect website. You'll want to keep your eyes on our friend Norbert, because every time he appears with questions like this, have your cue cards from the lesson guide and your brain ready to answer the questions he gives you. And teachers, when you see Norbert with a remote, that's your cue to pause the videotape and discuss the cue card questions.
Today, we're at NASA Johnson Space Center here in Houston.
Why? To learn about the International Space Station, or the ISS, and the people who make it work. The ISS is a huge laboratory being built in orbit. Scientists on the ground will send their research to the station to be performed by astronauts from all around the world.
There are 16 countries participating in the largest and most expensive laboratory ever built in space. By working together rather than competing, top scientists from around the world can collaborate and share information.
Using the United States Space Shuttle and various rockets from other countries, it will take more than 100 space flights to assemble the 100+ components of the ISS.
The ISS will be about the size of a football field. It will weigh approximately 1 million pounds, or over 100 adult elephants, approximately total the volume of a 747 jumbo jet, and generate enough power to light up more than 40 average homes.
How will the International Space Station get all that power?
From the sun. Giant solar arrays will capture the energy from the sun and convert it to electricity. We'll learn more about the parts of the space station and what they do a little later.
As we witnessed from the Expedition 1 crew, the first full-time residents on the ISS, the space station now supports human life. During Expedition 1's 5-month space stay, the crew of the Space Shuttle Atlantis delivered and installed the first U.S. laboratory, Destiny. This lab, built by the Boeing company at the NASA Marshall Space Flight Center, is the centerpiece for scientific research on the station and will support many experiments.
Space station crews will continue to rotate shifts every 4 to 6 months, preparing the station for the arrival of more components and beginning scientific research.
Why build an International Space Station?
Great question. If you'd like to study sound, you'd go to a quiet room. If you'd like to study light, you'd go to a dark room. And if you'd like to study the effects of gravity, you'd want to go into an anti-gravity room. But since there's no such thing on Earth, we have the ISS.
On board the ISS, a microgravity environment is created. This is where the effects of gravity are reduced compared to those experienced here on Earth. You see, the ISS is in a continuous state of free fall around the Earth, causing the astronauts and objects inside to appear to float and be weightless. You can experience free fall when you jump off a diving board. You are practically weightless until you hit the water.
But how does the space station stay in orbit if it's falling towards the Earth?
Here's an analogy. 300 years ago, a great scientist by the name of Sir Isaac Newton imagined an experiment in his head. He pictured a cannon on top of a very tall mountain. When he fired the cannonball would soon fall to Earth. But if he used a cannon with more power, the cannonball would go halfway around the Earth before it landed. And if he used a super-duper cannon, the cannonball would go so fast that it would fall at the same rate that the Earth's surface is curving away beneath it. This super-fast cannonball would never hit the Earth. It would be in orbit. And if you were sitting on the cannonball, you would feel weightless. NASA uses rockets instead of a cannon, and the ISS instead of a cannonball.
By understanding the effects of gravity, we can learn why things behave the way they do.
Take the human body, for instance. How does a microgravity environment affect the residents of the ISS? One of our guests will fill us in.
The ISS will also give students like you first-hand experience with the space program. Get this, from your own classroom, you can talk via amateur radio to the astronauts on board the ISS.
Or learn about Earth from the unique perspective of space with EarthCam, which stands for Earth Knowledge Acquired by Middle School Students. The EarthCam has already flown on 5 shuttle missions involving students nationally and internationally. Visit the EarthCam website to learn more.
And don't forget, later in the show you'll be constructing your own model of the ISS. But before we do that, let's learn about some of the parts that make up the space station.
How will a space shuttle attach to the ISS?
Describe 2 ways that the International Space Station will stay in Earth's orbit.
Describe the function of the solar arrays, thermal radiators, robotic arm, and truss.
I'd like to welcome NASA Connect this morning to the Johnson Space Center here in Houston. My name is Connie Van Prey-Kremens, and I work with the International Space Station program doing outreach and communications. What we're building in outer space is a world-class research facility. The United States NASA is the lead integrator of the program. ESA, the European Space Agency, the Russian Space Agency, the Japanese Space Agency, and the Canadian Space Agency all own the International Space Station, and as partners bring elements and people and training and research and all the facilities that we're building to our orbiting facility. In 1998, we began with a Russian-built, US paid-for module called Zarya. What it was is the initial power block and brains of the station. Soon after that, we launched Unity. That was a Boeing-built United States element. Unity is one of 3 connecting bridge modules that will be put on the International Space Station. After we put Unity up, came the service module. That's an entirely Russian element. It's Russian-built and Russian-launched. And the service module actually took over much of the functions that we had of Zarya. And it also is the place where the astronauts live, work, and sleep.
How does the shuttle dock to the space station?
Well, that's what Unity provides. Unity has 6 docking ports. So the shuttle comes up and docks to a pressurized mating adapter, which is attached to the Unity bridge. And then through there, supplies can be moved into the space station.
So how will the station get power for the astronauts to use?
From the sun. What the International Space Station has is a series of giant solar arrays, photovoltaic solar arrays. We have 1 set of arrays up there right now. There'll be 4 in total that be aligned along the truss.
What exactly is a truss?
The truss is a backbone girder-like structure, and you'll see this long, almost like steel beam crate box, and that is literally what these solar arrays are going to be attached to. It's what modules are hung from, and the astronauts will be walking along it. Also walking and riding along it will be the Canadian robotic arm system for the International Space Station. Attached to the arm is what we call a special dexterous manipulator system, or a very smart hand that can go along and pick up different parts, modules, and move it around.
Okay, so I know that the solar arrays are on the truss, but what are the other, panel things?
Van, you're probably talking about the thermal radiators. That's the heat rejection system. Much like an air conditioning system would function in your home, the job of these radiators is to collect the buildup of heat and power generated internally and use it to move that heat outside the space station and dump it into space so that we can maintain comfortable levels of working for the astronauts and for the systems.
Now, I know the ISS is in a state of free fall, Connie, but how does it stay up in orbit?
Well, initially, we have attitude control thrusters that will continue to operate throughout the life of the station. These are the little jets that use fuel to keep our attitude.
What do you mean by attitude control?
Well, Jennifer, the space station has to maintain a certain position as it's being constructed. We want to get the maximum exposure to the sun for the arrays, so the attitude control is what keeps this position of the station.
So how do you know the pieces are going to fit together when you get them in space?
Well, this is part of the miracle challenge that confronts the International Space Station program, because these major elements have to fit together with hairline tolerance the first time when they're attached in Earth orbit. All the flight elements are literally put in line on their way to get integrated into the shuttle. What we can't do physically, we're doing through software. In fact, controlling the International Space Station is going to take more than 2 million lines of computer code. And we're learning valuable things through that testing. We're fixing problems before they ever become a problem on orbit.
Thank you so much, Connie. Now that we've learned about some of the parts of the ISS, how would you like to build your own model?
But wait, there's a catch. You have a budget.
NASA Connect traveled northwest to San Francisco, California for this program's classroom activity.
Hi, we're from Alice Longview in San Francisco, California.
NASA Connect has asked us to show you this program's classroom activity.
You'll work in groups to design an alternative space station. Then you'll create a model using everyday items like aluminum cans, cereal boxes, and straws. You'll analyze and interpret data to determine the best design based on budget restrictions, weight, and placement of the parts that you construct. Teachers, make sure you download the lesson guide for this activity from the NASA Connect website. In it, you'll find a list of materials, directions, and student worksheets. We won't cover everything in the next few minutes, but we will give you a general idea about how it all goes together. To begin, your teacher will display the labeled picture of the ISS, as it may appear upon completion. Discuss each component and its functions.
Okay, the National Aeronautics and Space Administration needs your help. They want you to design and build a model of an international space station, and your budget is $1 billion.
Your first step is to construct the components. To power your station, you'll make photovoltaic or PV arrays using transparency film and craft sticks. The thermal radiators used to cool the station are made with aluminum foil. A cardboard tube serves as the docking port. The habitation and laboratory modules are made with aluminum cans. The truss segments used to connect the modules are made from foam food trays. A small cereal box represents the core module of your space station. Buttons are used to simulate the attitude control thrusters. And for the robotic arm, use a flexible drinking straw. Find the total mass and total cost of each component using formulas provided in the lesson guide and record the values on your student worksheet. Before you design and assemble your space station, you need to pay close attention to the constraints listed in Appendix A.
Okay, remember the budget for the space station is $1 billion. If you break a component or a section of the space station, you have to purchase a new one.
Now decide how all the components of your space station will be arranged. Make a sketch before you start your actual assembly, and don't forget your constraints. Use tape and glue to put it all together. When your space station is assembled, the next step is to calculate the total mass. Because the ISS is being assembled in orbit, and not here on Earth, it's impossible to get the total mass at one time. Therefore, NASA determines the total mass by taking the sum of the individual components before they are launched into space. Since we are working with a model, there are two ways to calculate the total mass. First, take the sum of the mass of the individual components, then use your balance to weight your completed model. Find the difference between the two masses and compare the accuracy of massing individual pieces with the mass of the entire space station. If the difference is greater than 5 grams, you'll be charged a tax of $1 million per gram. If the difference is less than or equal to 5 grams, then the space tax will not apply. Record any space tax on the data table. Finally, calculate the total cost of your space station by taking the sums of costs for all your components and any space tax you owe. Did you meet your budget, or are you over budget?
We would like to thank the San Jose AIAA student branch for helping us with this activity. If you would like to learn more about the AIAA mentoring program, check out the NASA Connect website.
So far, we've learned about a few of the parts that actually make up the International Space Station.
That's right, and you've been given the opportunity to put together your own model of the space station.
You know, I wonder how difficult it is for the astronauts to actually dock the shuttle to the space station.
Technology is the key. Let's connect to Shelley Canright and learn more. NASA Connect traveled northeast to Chicago, Illinois for this program's web-based activity.
You're right, Jennifer. Technology can and will transform the way we train and educate. And that's why I've brought you here to Chicago, Illinois, to introduce you to NASA Connect's museum partner, the Adler Planetarium and Astronomy Museum, and to tempt you to apply your hands and your minds to an online space flight experience. As you can see, Adler offers the public many different ways to learn about and to explore science and astronomy. We are now here in the Solar System Gallery, where students from Bright Elementary School and the AIAA student branch of the Illinois Institute of Technology have gathered and are waiting for you to introduce you to a new website created especially for NASA Connect by the NASA Classroom of the Future, which is located in Wheeling, West Virginia. Our friends at the Classroom of the Future have put together a unique experience that combines internet-based simulations, hands-on activities, and orbital mechanics.
Orbital mechanics?
No, it's not about fixing things in space, but it's how things like motion, acceleration, and force affect objects in space, like the planets, the moon, the stars, the U.S. Space Shuttle, and the International Space Station. So how about it, gang? Do you have the right stuff for this program's online challenge?
From Norbert's lab on the NASA Connect website, click on the Activity button. Here you'll find the first hands-on experiment designed to get you ready to use the web-based orbital simulator. Using a plastic ruler, 2 glass or metal balls, a few cans, masking tape, and a stopwatch, you'll be able to define the difference between steady motion and acceleration. This simulator gives you the opportunity to view 2 objects orbiting a planet or star. By adjusting the orbital radius of one of the objects, you can begin to explore how radius, speed, and orbital period are all connected. After using the simulator, you'll begin to understand how to answer this question. How can we use our knowledge of orbits to help the shuttle rendezvous with the International Space Station? The Shuttle ISS Orbital Simulator will get you ready for the actual docking activity you will do with your classmates. On this website, you will start with the shuttle and ISS orbiting the Earth at the same altitude and 90 degrees apart. The challenge is to determine the most efficient way to position the 2 objects so that they are traveling at the same speed and close enough to each other to perform the visual docking maneuvers. Now, let's start an activity that deals directly with the International Space Station.
I'm Don Watson. I'm with NASA's Classroom of the Future and part of their International Space Station Challenge website activity. Today we're doing a docking simulation. We're going to do that by actually building a docking simulator using an office chair on wheels, tripod, video camera, a docking grid mounted in front, and a TV. We're also going to do command and control with 2-way radios. We're having thrusters that are using ropes for control, and command and control is from Mission Control. Mission Control's only reference is the video image that they see on the screen. They give movement commands to the pilot. The pilot relays that information to the thrusters move, and hopefully we successfully rendezvous and dock to the space station. All additional information about how to construct the docking challenge and the chair and all activity-related material is at NASA's Connect website.
Bringing to you the power of digital learning, I'm Shelley Kienwright for NASA Connect Online.
Bye!
Technology really is the key to astronaut training and the tools they use.
Right, but what about the research being conducted aboard the International Space Station?
Yeah, and the microgravity environment. How does that affect the astronauts working and living in space?
Well, for answers, we came here to Building 9 at the Johnson Space Center.
What's unique about the research environment on the International Space Station?
How does zero gravity affect fluids in your body?
Describe the relationship between time and space and bone loss.
As the research manager for the ISS program here at the Johnson Space Center, it's my job to communicate with scientists who want to do research on board the space station.
I also work with the builders of the station to be sure it's both a well-equipped laboratory and observatory.
You see, the ISS is about exploration, human exploration.
It's the place where we will learn to live and work in space. It's where we'll establish a permanent human presence in space and advance human exploration of our solar system.
What kind of work will be conducted on the ISS?
Research. We will work on improving manufacturing processes, developing better health care, and researching tomorrow's products today. All this research will take place in the laboratories you saw earlier and in the unique, out-of-this-world environment of space. You see, the microgravity environment and the high vantage point for viewing Earth and the universe are unique. The permanent space station allows experiments to run for longer times than we used to on the space shuttle and gives scientists repeated access to these experiments. This research cannot be done on Earth.
Well, Dr. Bartow, it sounds like a microgravity environment will help scientists make new discoveries. But how will microgravity affect the people living on board the space station?
Great question, Jennifer. The human body reacts immediately and dramatically to the microgravity environment we feel when we go into orbit around the Earth.
Remember how you explained being on the station is like being in a state of free fall? It feels like there is no gravity. That's why we often call it zero-G. One of the first reactions of the body to zero-G is to push our internal fluids upward in our body. You see, on Earth, in 1G, our body works to push the fluids inside upward, so all the water, blood, and other fluids don't collect in your feet. When the body first experiences zero-G, it continues to push the fluids up, as on Earth, but since there is no 1G pulling down anymore, the upper body and head ends up with too much fluid. If you've ever seen pictures of us in space on the first day, our faces are puffed up like chipmunks because of the extra fluid in our upper body. But the body quickly senses this condition and begins to move the fluids to different parts of the body. In about 2 or 3 days, we reach a new point of balance where our bodies have less fluid in our bloodstream than the average person on Earth. If you return to Earth's 1G in this state, you would probably faint. To counteract that, we fluid load just before returning to Earth. For instance, we drink at least 1 quart of water within 1 hour of returning, along with salt tablets, which keeps the water from passing directly to your bladder.
Wow. Well, how else does microgravity affect the human body?
Well, Van, a longer-term effect, which also begins immediately, is the loss of bone mass. When you lose bone mass, your bones become brittle and can break very easily.
Anyway, only about 400 humans have flown in space, and only a fraction of them were tested carefully for bone loss. The numbers so far are startling. Healthy space travelers lose bone mass 10 times faster than people here on Earth. Whether in space for 1 week or 1 year, the rate of bone loss is about the same.
Let me show you how important math is when determining bone loss.
The percent of bone loss is a function of the length of time in space. L is the percent of bone loss, R is the rate of bone loss per month, and T is the time in space. So far, the data we've collected tells us that humans in space lose bone mass at a rate of 1% per month. The function L equals RT tells us that the longer you are in space, the more bone mass you lose. We have values of T up to 14 months, and the function appears linear. So far, we haven't had any astronauts in space for more than 14 months. This rate of bone loss could be a problem if we want to go on a 3-year trip to Mars and back. That trip would cause a bone mass loss of 36%. Our bones would be so brittle, any type of physical activity would be out of the question.
This is not good news. We wish the function would level off eventually with time, and further bone loss would stop.
So, how do you measure bone loss?
Well, we measure bone loss by conducting tests like X-rays on the crew, both before and after they fly.
Each person reacts differently to zero-G, so we need to put the data from many astronauts all together and use statistics to predict the effect on future crew members.
We calculate means, medians, and standard deviation. Our statistics so far are not that good because we have data on so few people.
You see, when you average data from only a few people out of a large group, the result from those few people may not match the average of the larger group. However, if you collect data on hundreds of people, like ground-based medical research does, the average is more reliable and easier to predict. Because there are only a handful of good measurements on space flyers, our predicted average is less reliable. We just need to make many more measurements.
We'll also study why we lose our bone mass. Then maybe we can develop drugs to stop the effect. In fact, the National Institutes of Health is working with us on this research. So you see, research on ISS is not only about improving life in space, but also improving life here on Earth.
Well, thanks so much, Dr. Bartow.
You're very welcome.
Earlier in the program, Jennifer and I said you could see the ISS in the sky from your own backyard. Visit this website to see if the ISS will be flying over your city.
Speaking of the internet, how would you like to take a virtual tour of the ISS from your own computer?
NASA Connect traveled northeast to NASA Langley Research Center in Hampton, Virginia to find out about the virtual International Space Station.
The Virtual International Space Station, or VISS, is an immersive, three-dimensional model of the space station that can be installed on your computer. Once installed, you'll be able to walk about the interior and fly around the exterior of the ISS as if you were on a spacewalk. The virtual environment is similar to virtual computer games you may play. You can take a tour of each module of the station and click on the red question marks for additional information. The VISS allows you to have a realistic astronaut perspective on what it'll be like to work and live in the station.
But Pat, why was the Virtual International Space Station created?
That's a good question. As you learned earlier, the space station will allow many different experiments to be conducted all at once. The problem is this can also make things difficult for the scientists and researchers. You see, there are hundreds and hundreds of documents that go into a bunch of detail about what the station can do. Scientists and researchers who aren't familiar with the station's capabilities would have to sort through all those documents to find out if the ISS could help them with their experiments. The VISS was created so potential users of the station, like scientists, can use their computer and actually walk up to an experiment facility on the station, just like he or she would do to a book in a library, then quickly skim information to see if that facility would help with their research. Currently, the VISS is the only publicly available 3D environment to introduce people to the many capabilities of the ISS.
That's awesome. How can we get the virtual ISS?
You can download the Virtual International Space Station at this website. Because the tour includes the completed International Space Station, the files are quite large, so allow some time to download them.
Well, you know, that wraps up another episode of NASA Connect. We'd like to thank everyone who helped make this episode possible.
Yeah, Jennifer and I are waiting for your questions, comments, and suggestions, so write us at NASA Connect, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia, 23681, or email us at connect@edu.larc.nasa.gov.
Teachers, if you would like a videotape of this program and the accompanying lesson guide, check out the NASA Connect website. From our site, you can link to CORE, the NASA Central Operation of Resources for Educators, or link to the NASA Educator Resource Center Network.
Until next time, stay connected to math,
science,
technology,
and NASA. See you then.
See you.
So you see, research on ISS is not only about improving life.
I'm so sorry.
Great question. Sorry. If you'd like to study light, you'd go into...
And telling people what we're doing. That was horrible.
Hey, that's not good though.
You know what we're doing? I'm going to tell you what we're doing. Oh, we're doing this. Well, that's what we're doing. Okay.
Describe the functions of the solar array's robotic... I messed up. Hold on.
Currently, the VISS is the only publicly available 3D model of the space station that tells people what station can do.
Wow. Cool.
Busted. And it's so big that sometimes you can see it travel across the sky.
That's right. Later on in the show, we'll tell you wow.